Okay, let's continue with the classical systems. We were discussing how to specify the state of these systems. Of course, we know from our classical mechanics that the coordinates change in time, and we know how they change in time. The contact with the classical mechanics gives us the way the positions are changing with time. dq dt should be related to the Hamiltonian of the system. And the momenta pi dot will be minus del h function of positions and momenta del qi. Again, I from 1 to 3n components are changing like this. That is the Hamiltonian of the system. We know the description quite well. Of course, as I've told you, a finite volume limits the positions. And a finite energy limits the momenta, the values momenta will have through the Hamiltonian, of course. Okay. Now, if you know the total energy of the system, you can, for example, if it has a precise value, E, these trajectories in phase space, okay, determined by these equations, the way they change, the picture that you have to have in your mind is that these representative points are moving around in the available phase space, aren't they? They describe trajectories. These are then will be restricted. Well, restricted to a hypersurface, for example, if the energy is fixed, through the Hamiltonian, and that should be equal to that precise value of the energy, total energy of the system. So that tells you how the trajectories are restricted. Well, if total energy E is in this range, usually that's what should be done. We cannot really fix it precisely to a value. Think about that experimentally, how difficult to define or fix the energy at a single value. You can fix it in between this limits, that means in a shell, energy shell of width delta, it is really another way of saying that the energy is fixed, isn't it? If delta is small, there isn't a big change in energy. It is a fixed energy. You can look at it that way. If that is the case, then energy is, the trajectories are fixed in a hypershell. Now the question is, how are you going to define this collection of points in phase space? You have to introduce a density function. The overall picture can be described by a density function. And this is defined in such a way that this quantity is the number of representative points in volume element that's the definition of density function. Now, this density function is going to take us to the average of a quantity. Since we are after averages for a large number of particles, that's the only thing we can do about physical properties. Ensemble average of a quantity, then, let's show it by the average of the quantity f, or function f, if you like, whatever is this physical property. That average can be written in terms of the quantity itself as a function of position and momentum, and the density function just to normalize it, so in some sense, this takes the place of probability, isn't it? We have a continuum, where we call it phase space, the trajectories of particles in this phase space. A portion of this phase space is occupied by our system. we can take averages by using this density function. Of course, density function is going to depend on the type of systems you are interested in. For example, if you are interested in micro-canonical systems, this is going to be constant if the given condition is satisfied on total energy. If the energy of the system is in this shell you are defining, or if it is fixed, then the rho is constant and zero otherwise. There is nothing if the condition is not satisfied. And if you are dealing with the canonical system, of course, it will be proportional to e to the minus beta h, the Hamiltonian, just like the Boltzmann factor we have found for the probability. I'm going to do both cases, but today I'm going to concentrate on the microcanonical systems. Okay? Canonical is the next chapter. Now, what are we trying to do? Let's try to see what's the aim for a microcanonical ensemble. I should be after the total number of microstates available to the system, isn't it? Logarithm of which will be proportional to the entropy. So I am, in general, after this number, finding the total number of microstates available to the system to go to the entropy, to go to the thermodynamic properties. But what do I have at hand? A volume in phase space, a volume of 6 n-dimensional space. If I know this, then to go to the number of states, microstates available to the system, I have to know a fundamental volume corresponding to a single state. Then I divide the total volume to this volume per state. I have the number of states, isn't it? So if I can calculate the total volume of phase space available to my system, microcanonical system, and if I know the fundamental volume of that space available to a single state, then I can get the total number of particles. And from there, I can get my thermodynamics. Is the mental map okay? What we are doing, what are we trying to do? That's what we are after. Now, let me call this total volume available to my system omega. So I'm trying to find this number whose logarithm is going to give me the entropy. If I know the total volume of phase space, available to my system, divide by the fundamental volume corresponding to a state per state. Then I have the total number of microstates So I can go from here to entropy, TB ln of gamma, in some sense, gives me the thermodynamics. That's my program now. Well, we know how to calculate the volume and surface of a 6n-dimensional space. I will give you a homework, which I'm not going to collect for this. It is in your book. The important thing is, how are we going to find the fundamental volume? What is this fundamental volume? In classical mechanics, we have a difficulty in defining this volume, because in classical mechanics we have x, y, z, px, py, pz, a single mathematical point as the state of the system, or the state of a particle, isn't it? But a mathematical point doesn't have a volume, isn't it? So how can I define a fundamental volume that will correspond to a state, a single state? What is the volume occupied by a single state? For that, I have to go to quantum mechanics and bring in a quantum mechanical idea, important idea of uncertainty principle, isn't it? Well, there is a limit to what we have to know for position and momentum. We cannot possibly know simultaneously both the position and momentum of a particle, isn't it? That's uncertainty principle. There is a limit that can be described as well, or you can think about this as dx, dy, dz, roughly speaking, dpx, dpy, dpz. This is going to define a fundamental volume. What will be the result for this? Of the order of what? Isn't it? A small number to the cube is even smaller, but that must be the fundamental volume. So this must be our omega zero. If you want to define a volume occupied by a particle instead of a point in phase space, it must be this minimum volume, isn't it? So all I'm left with to get to the number of states available, microstates available to your system, that. So all I have to know is the volume of this phase space then. If I know this fundamental volume, here comes the homework. It is appendix in your book. You should read your book. For a single particle, that's what we have done. Well, the ones that I have distributed, I will collect them, okay? You should hand it in before that time, or at that time. And this homework is just what you should do at home. You don't have to hand that in. So, here is the homework. It is a reading assignment, if you like. Find the volume and surface of an n-dimensional sphere of radius r. This is appendix C of Patria. And the answers are volume of n-dimensional space, or sphere of radius r is given by pi n over 2 factorial times r to the n. You know the answer for 3 dimension. What was it? 4 pi over 3 r cubed. It gives, this thing gives that. And the surface of the sphere is 2 pi n over 2 gamma n over 2 r n minus 1. In 3 dimension, you know that it's 4 pi r squared, isn't it? Surface of the sphere. Very simple. I think you should read this appendix and try this result. I'm going to use it in a moment when I am dealing with the examples. I will give you some examples of systems where we can calculate this volume divided by the fundamental volume to get the number of microstates available to the system, and then get the thermodynamics. Well, my first example is the classical ideal gas, of course. Let's apply this ensemble average ideas to an ideal classical gas as a first example. Do we have any questions up to now? Okay. So, Let's consider non-relativistic. Free particles. Classical ideal gas. That means each particle only having a kinetic energy and nothing else. They are not interacting. There's no potential energy. If you put it into a box, of course, the shape of the box can introduce a potential energy. You are just fixing it in a potential. You can use that, but these are free particles. And the Hamiltonian for the system is nothing but sum over all these kinetic energies. Particles are considered to have the same mass, identical particles, collection of identical particles. That's the Hamiltonian. Now, what type of phase space you expect for this? The shape of the phase space occupied by particles. They are moving in all directions freely, so they describe a sphere, isn't it? When you think about momentum, the direction of motion in all directions, so phase space is nothing but having a shape of a sphere. Now, can we find the radius of the sphere? I think we can. It's coming from, of course, the energy. Total energy is going to define the radius, isn't it? Of course, that must be corresponding to the maximum possible momentum. And of course, since we have square of momentum, this must be the radius squared. So this R is the effective radius of the region occupied by your system, isn't it? Limited by the total energy. Is that okay? So, let's calculate the total volume in momentum space. I gave you the expression from your book. That is pi 3n over 2 r to 3n divided by 3n over 2 factorial, isn't it? That's the expression for the volume of r dimension radius sphere of radius r. So, and r is square root 2m capital E, defined by the maximum energy of the system. So this then can be written as, using that, as v to the n well, of course, we have to include the this is in momentum space. Position space each is going to have v, so v to the n is the contribution coming from the position space. Okay? This is total volume. Omega, in other words, isn't it? V to the n, and this volume in momentum space, 3n over 2, 2me, 3n over 2, divided by 3n over 2 factorial. We have the total volume. This is the total volume available in phase space. We have done momentum and position spaces separately and collected them together. So, we can go from here to the number of microstates because we know the fundamental volume corresponds to a state therefore the number of microstates available to the system, well, I have to divide this by what? H cubed to the power n, isn't it? We have n particles. Per particle I did, it was h cubed, h to the 3n. So v over h cubed to the power n. And the other things also 2m pi e to the power 3n over 2. 3n over 2 factorial. It's like magic, isn't it? We found the total number of microstates available to our system of classical gas now, of n particles. Is this okay? Do we have any problems, questions? Okay. Now, if this is the case, the logarithm, well, we know the logarithm 3n over 2 factorial is approximately Stirling's approximation, 3n over 2, ln 3n over 2 minus 3n over 2, isn't it? Ln n factorial is n ln n minus n. Using this, you can get to logarithm of that. N ln v over h cubed 4 pi n energy over 3n 3 over 2 that's the logarithm. I just have to multiply it with Boltzmann constant, isn't it? KB. So I have the entropy. I have completed my program going from total volume of phase space available to the number of microstates available to my system. Entropy, KB, ln gamma. So it is NKB ln Can I go from here to the energy? Of course, I can write energy in terms of entropy by exponentiating. Huh? There's logarithm, so I can get rid of that. So I can rewrite as follows. That thing must be equal to 2/3 logarithm v over h cubed if I exponentiate both sides, I get the following: e to the 2s 3nkb minus 1. Entropy is measured in units of nkb anyway, so the exponent is dimensionless, just a number. It must be dimensionless, that's a number, minus 1. So that turns out to be v over h cubed 2/3 4 pi m over 3m e, and that gives me the energy. Oh, wonderful. So I find the energy as that's my energy. Well, the mathematical part is quite easy, so I'm not going to concentrate on this. It is an easy calculation. If you know the volume of n-dimensional sphere, you can easily get to this. But what about the thermodynamics? Can we get from here to equation of state, for example? For classical gas, what was that equation of state? P times V is equal to nkBT, isn't it? Can I get to that? Or what is the energy? What do we expect for total energy of this system? 3/2 nkBT. Let's get that result. How are we going to get it? The first law and second law combined gives us this, isn't it? And that tells me, or gives me the temperature of the system as dEds, keeping V and N constant. If I keep them constant, they drop, isn't it? TDS is equal to the dEds. If I take derivative of this with respect to S, I will get the temperature. Let's do that. Well, derivative of exponential is very easy. What is in the exponent comes down. You have exponential again. So this gives you E times 2 over 3 nkb. Since you are going to get exponential back, you are going to get the exact expression there, isn't it? Here. That's the exponential giving you the the energy expression. So that's the multiplier comes from the derivative. Okay? So it says exactly E equals 3 over 2 n kBt, isn't it? Exactly what you expect for a classical gas, non-reduced classical gas. And you can also calculate pressure, and you know how to calculate pressure. It is T del S del V, keeping E and N constant, and you can do that. Take derivative with respect to volume. That gives you nothing but PV equals NKBT. Everything you expect comes out to be correct. It should be. And these general expressions should come out to be correct whether you are dealing with microcanonical, canonical, or grand canonical ensembles, aren't they? Physics will not change of a classical ideal gas. Is a classical ideal gas, whatever ensemble you consider. But here, in microcanonical ensemble, the total energy will remain a constant, but in canonical, it will fluctuate, isn't it? Because there is an exchange of energy, and that fluctuation can be computed, as we are going to do in a moment, okay? When we deal with canonical ensembles. That's it, the main idea, and its application to a specific system. To make it richer, I will apply it to other problems too in my next lecture. Do we have any questions? You should ask questions. Okay? Let's give a break. Thank you. And it will get richer. It will get richer as we go along.